You know that feeling you get when you're scrolling through your phone and you stumble on a headline that makes your heart skip?
Yeah.
That's where we are right now. 3 days ago, astronomers monitoring objects in near-Earth space detected something that should never happen. An object cataloged as 3I/Atlas, a comet that's been wandering through our cosmic neighborhood for millennia, has fundamentally altered its trajectory. It's no longer on a safe, predictable path that would carry it harmlessly past Earth. No, it has changed course, and now it is heading directly for our orbit. Let me say that again, because the weight of those words deserves to sit with you. It is heading directly for our orbit. This is not a Hollywood scenario. This is not a drill. This is not science fiction. This is the moment when the universe reminds us that we live on a rock hurtling through space, surrounded by other rocks, and sometimes those rocks decide to come visit. So what exactly is 3I/Atlas? And more importantly, what does this mean for the roughly 8 billion of us living down here? Let's start with the cosmic biography of our unexpected visitor. Back in 2017, we detected the first interstellar object to ever pass through our solar system. We called it Oumuamua. It came from another star system, slingshot around our sun, and disappeared back into the cosmic void. It was a reminder that the universe is vast and weird and full of surprises. Scientists loved it. The public found it fascinating. And then it was gone and we moved on. But in 2019, something happened that made astronomers pay even closer attention. Another interstellar object showed up, Comet 2I/Borisov, and it came from a different star system entirely. Suddenly, we weren't looking at a 1 in a trillion event. We were looking at a pattern. The galaxy was sending us visitors. This shifted everything about how we monitor near-Earth space. We started funding more asteroid detection programs. We upgraded our telescopes. We built networks of robotic observers that work 24 hours a day, scanning the sky for anything approaching Earth's neighborhood. And that's what led us to 3I/Atlas. 3I/Atlas was first identified in 2021, approaching our solar system from the direction of Proxima Centauri. Now, Proxima Centauri is our closest stellar neighbor, just 4.24 light-years away. In cosmic terms, that's practically next door. In human terms, that's impossibly far. Light from Proxima Centauri takes over 4 years to reach us. But objects can travel between stars. They can be ejected from planetary systems. They can wander through the void for billions of years. And sometimes, by the mathematical accident of celestial mechanics, they find themselves on a collision course with our little blue planet. Here's the thing about comets that most people don't understand. They're not like asteroids. Asteroids are mostly rock and metal, dense, solid objects that have been hanging around since the birth of our solar system. Comets are something different entirely. They're what Carl Sagan called dirty snowballs. They're primarily composed of ice, water ice, methane ice, carbon dioxide ice, mixed with rock and dust and organic compounds. They form in the cold outer regions of solar systems, where temperatures are frigid enough for these volatiles to remain frozen. But here's what makes comets truly interesting. They're ancient. Some of them date back to the early formation of their home solar systems. They contain molecules that haven't changed in billions of years. They're time capsules from the birth of worlds. And when they approach the sun, when they enter the inner solar system where our planet lives, they begin to warm up. The ice doesn't just melt, it sublimates. It transforms directly from solid to gas, creating those magnificent tails that make comets some of the most visually stunning objects in the night sky. 3I/Atlas has been approaching our solar system for nearly 3 decades now. Astronomers have been tracking it, predicting its path, calculating where it would go. Every model suggested the same thing. It would pass roughly 200 million kilometers from Earth. That's significant, sure. In cosmic terms, it's relatively close. In human terms, it's about a third of the distance from the Earth to the Sun. It would be visible from Earth. Through a telescope, it might be quite spectacular. But it posed no danger whatsoever. Until Tuesday. That's when the data changed. On Tuesday morning, the Automated Astronomical Monitoring System, a network of automated telescopes scanning the sky from multiple locations on Earth, collected a set of observations that contradicted everything we thought we knew about 3I/Atlas. The object's trajectory showed acceleration that couldn't be explained by solar gravity alone. The brightness fluctuations suggested a massive outgassing event. And the spectroscopic data, the light signature that tells us what an object is made of, showed something we had never seen before in a comet approaching Earth space. The comet was already beginning to sublimate. Despite being still millions of kilometers away, outside the zone where solar radiation should have triggered significant outgassing, it was already ejecting massive quantities of material. It was already waking up. And that ejection of material was providing thrust. Not much thrust, but measurable thrust. It was changing the comet's vector. It was pushing 3I/Atlas toward a direct encounter with Earth's orbit. Now, I need to be very precise about what direct encounter with Earth's orbit means, because this is where panic often obscures understanding. The comet is being pushed toward the orbital path that Earth travels. But Earth doesn't occupy that entire orbit simultaneously. Earth is a point moving along that path. For a collision to occur, two things have to happen. The comet has to reach that point on the orbit, and Earth has to be at that same point at the same time. Think of it like two runners on a circular track. The track is Earth's orbit. Earth is one runner, moving steadily around the track at a constant speed. Now imagine another runner, that's the comet, approaching the track from outside. If both runners reach the same point on the track at the same moment, they collide. But if one reaches that point and passes through it before the other arrives, no collision occurs. So the immediate question becomes, where will Earth be when 3I/Atlas reaches our orbital path? According to our latest calculations, and these are calculations that are being updated hourly as new data comes in from observatories around the world, the comet will reach the orbital distance of Earth approximately 473 days from now. That's roughly 15.5 months. On the date of closest approach, Earth will be almost exactly on the opposite side of the Sun. We're safe. For now. But understand what I just said. For now. That changes the entire context of this conversation. Doesn't it? Because the thing about comets is they're not predictable the way asteroids are. Asteroids are inert. Once you know their velocity and position, you can calculate where they'll be forever. Comets are actively degassing. They're ejecting material. They're experiencing thrust from that ejection. They're also experiencing something called the Yarkovsky effect, where differential heating from solar radiation creates subtle forces that change their trajectory. They're also affected by solar wind. And if they pass close enough to planets, they're affected by gravitational perturbations from those planets. In other words, the more closely a comet approaches a star system, the harder it becomes to predict where it's going to go. Right now, our models show 3I/Atlas will pass approximately 37 million kilometers from Earth at closest approach. 37 million kilometers. That's about 97 times the distance between Earth and the Moon. To put it another way, if Earth were the size of a marble in your hand, the comet would pass about 200 meters away. Safe, but not impossibly safe. The real question is, what happens if the outgassing pattern changes? What happens if this comet experiences even greater sublimation as it gets closer to the Sun? What happens if we discover, in the coming months, that our calculations were incomplete? That's what has the scientific community genuinely concerned. Not panicked, concerned. This is the difference between alarm and the rational assessment of risk that defines real scientific work. Let me paint you a picture of what we're doing about this right now, because this is where the story becomes genuinely fascinating. Last night, NASA activated its Planetary Defense Coordination Office. This is not a small thing. The Planetary Defense Coordination Office exists specifically to prepare Earth for potential asteroid or comet impacts. They've been working for years on protocols for this kind of situation. Now they're putting those protocols into action. Every major astronomical facility on Earth, and I mean every single one, has been tasked with continuous monitoring of 3I/Atlas. The Hubble Space Telescope has already had its schedule reorganized to obtain images every 6 hours. The James Webb Space Telescope is currently taking spectroscopic measurements that will tell us exactly what gases the comet is ejecting and at what rate. Radio telescopes are analyzing the dust particles being ejected, measuring their velocity and composition. Simultaneously, scientists at universities around the world, in Beijing, in Moscow, in Cambridge, in Tokyo, in Sydney, are running new computational models incorporating all available data. They're using artificial intelligence to predict outgassing patterns based on the comet's composition. They're revising our trajectory calculations constantly. The goal is simple: reduce uncertainty, give ourselves a clearer picture of what's coming. But here's what I find genuinely beautiful about this moment, and I want you to understand this. The world is responding correctly. There's no conspiracy. There's no cover-up. There's no secret government plan to hide this from the public. Why? Because something this significant cannot be hidden. Astronomy is inherently transparent. Our telescopes are distributed across the entire planet. Professional and amateur astronomers everywhere are collecting data independently. If one group tried to hide information about an approaching comet, another would immediately detect the object themselves. The universe doesn't care about national borders or political interests. The comet will be what it will be, whether any government wants it to be or not. And that's why the coordinated global response we're seeing is actually a reason for measured optimism. I want to talk about impact probability for a moment, because this is where people often get confused about numbers and statistics. Right now, based on our best current models, the probability of 3I/Atlas striking Earth is approximately 0.0003%. That's one chance in about 3 million. To put that into perspective, you're more likely to be struck by lightning. You're more likely to be dealt a royal flush in poker. You're more likely to win a significant state lottery. So when I say the probability is negligible, I mean it statistically. But here's the crucial addendum. That probability is based on our current information, and our current information could change. As the comet gets closer, as we collect more data, as we refine our models, that probability could go up or down. Our job in the astronomical community is to make sure we're reducing that uncertainty as much as possible. Could it go up significantly? Theoretically, yes. If we discover that the outgassing we're observing is just the tip of the iceberg, if we find that the comet's composition is such that it will experience much more dramatic sublimation as it approaches the sun, then yes, that probability could increase. Could it drop to effectively zero? Absolutely. That's also very possible. This is the uncertainty principle of observational astronomy. You're always looking at incomplete data. You're always trying to fill in the gaps. And you're always hoping that tomorrow's observations reduce uncertainty rather than expanding it. Now, let's talk about what an impact would actually mean, because this is where Hollywood and reality diverge dramatically. If 3I/Atlas were to impact Earth, the effects would depend almost entirely on one variable: size. And we don't actually know how big this comet is with precision. Our current estimates suggest a nucleus, that's the solid core of the comet, the actual object of rock and ice beneath all the outgassing, somewhere in the range of 2 to 8 kilometers across. Let me give you some context. The comet that impacted Earth 66 million years ago, the one responsible for the extinction of the non-avian dinosaurs, was approximately 10 kilometers in diameter. That impact released energy equivalent to 10 billion nuclear bombs. It created a global winter that lasted years. It fundamentally altered the course of biological evolution on this planet. If 3I/Atlas is on the smaller end of estimates, 2 kilometers, it would still be catastrophic but regional rather than global. An impact in an ocean would create a tsunami. An impact on land would create a crater tens of kilometers across and vaporize everything within several hundred kilometers. But the global effects, changes to climate, to atmospheric composition, to biosphere stability, would be limited. If it were on the larger end of estimates, 8 kilometers, then yes, we're in extinction event territory. We're talking about genuine civilization-ending impact. We're talking about the kind of event that would require serious planetary defense measures. Now here's the thing, we know the tools exist to prevent this. They're not fictional. They're not speculative. They exist right now in 2026. The first option is called kinetic impact. You take a spacecraft, doesn't have to be enormous, doesn't have to be particularly sophisticated, and you aim it at the comet. You accelerate it to whatever velocity you can manage and you hit the comet with it. The impact transfers momentum. The comet's trajectory changes. Depending on how much warning time you have and how much velocity you can achieve, you could shift the comet's path enough to miss Earth entirely. NASA has actually tested this. The Double Asteroid Redirection Test DART deliberately impacted the asteroid Didymos 2 years ago, and it worked. The impact changed the asteroid's trajectory more than we expected. This is not theoretical. This is demonstrated fact. The second option is called gravity tractor. You position a spacecraft near the comet, not touching it, just being near it. The gravitational attraction between the spacecraft and the comet is tiny, but it's consistent. Over months or years, that tiny gravitational force gradually shifts the comet's trajectory. It's slower than kinetic impact, but it's also less risky because it doesn't involve violent collision. The third option is called ablation. You direct a laser or focus solar energy at the comet's surface. The surface material vaporizes. That vaporization is directional, it creates thrust. Again, it's subtle, but over time, it changes the comet's trajectory. Now, could we actually execute any of these solutions if we needed to? That depends on how much warning time we have. If 3I/Atlas becomes a genuine threat years in advance, absolutely. We have time to build a spacecraft, launch it, execute the deflection mission. But if we discover a week before impact that we're in real danger, then no, we couldn't do it. This is why these next months are crucial. This is why every observatory on Earth is focused on this comet. We need to reduce uncertainty. We need to nail down the trajectory as precisely as possible. We need to understand the outgassing pattern. Because in a scenario where the comet does become a genuine threat, knowledge is our first and most essential defense. Let me be very direct about what I think many people are actually worried about right now, because I think it's important to address the anxiety beneath the surface. When you hear that a comet is heading for Earth's orbit, the first thought that pops into your head isn't, what does the science tell us? It's, am I going to die? That's a deeply human response. That's legitimate, and I want to address it directly. The statistical probability of you personally being killed by 3I/Atlas is so small that it enters the realm of rounding error. You're statistically guaranteed to face more dangerous things this week than this comet represents. Your drive to work is more dangerous. The foods you eat carry more cancer risk. Crossing the street is more dangerous. But statistics don't comfort us the way they should. We're not good at thinking about probability. We're great at thinking about possibility. Our brains have evolved to recognize threats and respond to them. We're wired to see danger and react. This is why movies about asteroid impacts terrify people, while the actual statistical likelihood of impact is tiny. So here's what I'm asking you to do. Separate the scientific scenario from the emotional response. The science tells us this comet probably won't hit Earth. The science is strong. It's based on observation. It's updated hourly. And the science is what we should trust. What's happening in the media right now, and I've been paying attention to this, is there's a tendency to amplify the word urgent and direct without enough context about what those words actually mean in an astronomical sense. Urgent in astronomy might mean, we need to refine this calculation within 6 months. It doesn't mean impact is imminent. Directly heading for Earth's orbit means it's going to intersect the path that Earth travels. But it doesn't mean it's heading for Earth itself. It's a subtle distinction, but it's an important one. Let me tell you what's genuinely remarkable about this situation. In 1995, if we discovered a comet on a potential collision course with Earth, we would have had limited options. Our ability to predict impact probabilities was less precise. Our computational models were less sophisticated. And our technology for responding to threats was barely in the experimental phase. In 2026, if we discover that 3I/Atlas is a genuine threat, we have options. We have the technology. We have the capability. We have a global community of scientists and engineers who are prepared to work on this problem. We have spacecraft that can be constructed and launched. We have deflection technologies that have been tested. We have planetary defense protocols that are now being deployed. This is a situation where advancing technology gives us agency. This is a situation where science and engineering can protect us. And this is a situation where international cooperation is already happening, without prompting, because we've all realized that a comet doesn't care about borders. I've spent a lot of my career trying to get people to understand that we live in a cosmos, that we're part of a system that's vast and complex and beautiful and, yes, sometimes dangerous. Moments like this, moments when a comet approaches and we have to collectively focus on understanding it, these moments remind us that we're all in this together. We all share a single planet. We all share a desire to understand what's happening around us. And we all share a responsibility to respond thoughtfully and scientifically to whatever the universe throws at us. Right now, the universe is throwing a comet at Earth's orbit. We're responding by observing it carefully, collecting data, sharing information, and preparing contingency plans. This is civilization at its best. This is humanity actually getting something right. Do I think 3I/Atlas will hit us? No. The science strongly suggests it won't. But do I think it's important that we're treating this threat seriously, even at low probability? Absolutely, because there will inevitably be future threats. There will be asteroids. There will be comets. Some will be larger. Some will have shorter warning times. Some will give us less opportunity to respond. And our response to this comet, our practice in the theater of planetary defense, might save billions of lives when a genuine, higher probability threat arrives. Let me tell you about the longer-term context here, because I think it matters. The solar system is not a quiet place. It never has been. This is a system where objects collide, where gravitational influences bend trajectories, where the dynamic interactions of planets and asteroids and comets create an essentially chaotic landscape. Over the history of Earth, over the last 4.5 billion years, we've been impacted by asteroids and comets repeatedly. Some of these impacts have shaped life on our planet. Some have ended dominance of entire biological groups. And some have left barely a mark on the geological record. We live in an environment where impacts happen. They're not common on human timescales, but they're not unimaginably rare either. If you live on Earth for long enough, if human civilization persists for hundreds of thousands of years, we will face a significant impact threat again. That's not pessimism. That's basic probability applied to cosmic mechanics. Which is why what we're doing right now, building the technology, developing the protocols, training the personnel who would respond to an impact threat, this is among the most important work that humanity can do. This is what ensures we're not a one-impact species, a civilization that got lucky once and then didn't survive the second time. This is long-term insurance. This is evolution applied to civilization. What happens over the next 15 months is going to be fascinating. We're going to watch this comet approach. We're going to see it brighten as it gets closer to the sun. We're going to see its tail develop, that magnificent, glowing feature that makes comets so visually distinctive. We're going to see it transform from an object of academic interest into something that might be visible from Earth with the naked eye or with binoculars. We're going to experience wonder. And simultaneously, we're going to be doing serious science. We're going to be refining our understanding of this object. We're going to be improving our models of cometary behavior. We're going to be advancing our capability to predict trajectories and assess risks. And if the probability of impact increases significantly as new data emerges, we're going to be prepared to respond. The comet doesn't know we exist. It doesn't know we're watching it. It doesn't know we're calculating its trajectory and assessing the threat it represents. It's just a lump of ice and rock, following the laws of physics, doing what ice and rock do when they move through space under the influence of gravity and radiation. But we know it's coming, and we're ready. That's the remarkable thing about living in the 2020s. That's the remarkable thing about having developed the tools of science and technology and global communication. We can see threats approaching. We can analyze them. We can model them. We can prepare for them. We can, if necessary, do something about them. This Comet 3I/Atlas is coming. It's changing course. It's heading toward Earth's orbit. And we're watching, we're calculating, we're preparing, and we're hopeful. Because hope combined with science, that's the most powerful thing humans possess. The universe is vast. The cosmos is dangerous. And we are not defenseless. We are informed. We are technological. We are capable. And right now, in this moment, as a comet approaches our world, We are united in our determination to understand what's coming and to protect what we've built. Whatever happens next, we'll face it together. And we'll face it armed with knowledge. That's the real story here. Not fear. Knowledge. Not despair. Hope. Not powerlessness. Agency. Comet is coming. And humanity is ready.